Now let's get back to this example, which we sort of started out with as a motivational idea, but now we're going to actually do it. So I'm rotating around the y-axis. Imagine having this thing, kind of looks like a thumbprint cookie, you know. And I said what I'm going to do is I'm going to do it with a cylindrical shell. So here's my y equals sine of x squared. And my cylinder is going to look like this. So this is the radius, and this is the height of the cylinder. So my formula was 2 pi times the radius times the height times d thickness. Okay, in this case, I've got 2 pi times the radius is going to be, right, this is the x direction and this is the y direction. So we can see going to this point, the radius is going to be x. The height is going to be y, but we can put this in for y, right? So x sine x squared, and thickness is going to be the same direction as radius, so dx. Now, because my variable is x, I use the coordinates, like the limits in x, so 0 root pi. Okay, now I can do this integral, and the reason I can do this integral, the reason I'm saved, right, is because I have this x. In fact, I even have 2x, right? So I can do this with a simple u substitution. U equals x squared, du is 2x dx. So let's just go ahead and do that. It's just going to be sine u du. Now, when x is 0, u is 0. When x is root pi, u is going to be pi, right? So then I take my integral. The derivative of negative cosine is, the integral of sine is negative cosine. The derivative of cosine is negative sine, right? So this is from 0 to pi. And that actually evaluates, this is minus, right, cosine of -1. So this anyway evaluates at 2 pi. A nice answer. Whoops. Let's see if you can see the 2. So once we were able to set it up, it wasn't too bad. So I'm going to keep this up here because that's the same formula for everything. Now I'm going to do another example, but we're going to be rotating around the other axis. We're going to be rotating around the x-axis for my second example. So let's see, where was this example? We want the region between x equals 1 plus y minus 2 squared and x equal 2. Rotated about the x-axis. Okay, so this isn't, well, let me see what here. Here. Turns out, 1, 2, 3, 4, 5. Well, you draw the thing, right? So x equals 2. Could have drawn it big. I'm going to draw it bigger. This is going to be too small. The actual region here, like this is just a regular old parabola facing this way. The actual region isn't very large because this parabola, its vertex is here, and you go through here, and it looks like that. Of course, you need to check that, right? So double check that I did it properly. I can see what I have here. I've got 2 equals 1 plus y minus 2 squared. So I have 1 equals y minus 2 squared. And if you solve for that, you will get that y equals 1 and 3, obviously. So these 2 points are exactly what they look like they are. You've got 2, 1 and 2, 3. Okay. Now, when I wrap this around, of course, you're going to have something which looks like somebody took a donut and sliced it this way, because it's going to be, I always talk about food, right? Thumbprint cookies, donuts cut in half. What can you do? It's because I'm in the kitchen. Not cooking, mind you. You don't like to do that. Okay. Anyway, so this is our sort of our cross section, and you imagine this shape going all the way around. And again, this is one where, yeah, this one you probably could do with the washers, but you have to mess around with it quite a bit because the outside and the inside are the same curve somehow. So this one lends itself nicely to the cylindrical shell. So my cylindrical shell is now going to look like this. So I chose this one, of course, because it's in the opposite direction, right? We're going around here. I forgot to write the arrow, but I forgot to write the X. Sorry about that. Said it, didn't write it. And my thing looks, oh, it just looks totally off because I drew it badly. So it looks totally off. Hold on, let me fix. We can fix that, sure we can, because this one would be over here, right? What am I doing? There we go. A little better. Okay, in any case, you can imagine this shell, so think about that like a soup can with no top and bottom. It's going to have this thickness here, right? If I look at this thin shell, this is actually going to be the height because the circles are here, so that's where it's open, right? And this is going to be the radius. So in this case, the radius is going to be y, and the height is going to be x. Something x, right? This x minus that x. Okay? So you have to be a little bit careful. This x minus that x. So let's go ahead and get that straightened out first. So the radius, as we said, was y. That means that we're going to be, our d thickness is going to be y. We're going to be integrating with respect to y. So this is y, and this is dy. Now, so far so good, right? Now, what about the height? Because if I just put in x, right, I'm getting, think about this curve. If I just put in x here, I'm getting this distance here. So that's not what I want. I want this distance here. What I really want for height, it's going to be, if I look at it, I want 2 minus this distance here. So again, you really have to think about this as the difference between two curves, sort of. The bigger curve is the line, and the smaller curve is this parabola. So this would be x, right? X up here. So here my height is actually, say, x out minus x in, or x right minus x left. Very similar to what we did when we did washers, right? Because it was like the outer curve minus the inner curve. So this is the same thing. The thing is, it may be a little bit harder to see until you get used to it thinking about that. Okay? So the right-hand side, x is just the 2. Let's see if we can keep that. The left-hand side is this inner part. It's this x. So 2 minus 1 plus y minus 2 quantity squared. There. So that's actually the height in this case. Maybe I should have picked a more straightforward example, huh? I guess I just wasn't thinking. We'll do another one. Like that. Okay, and now the limits, we found them way back here, right? The limits go from 1 to 3. It's the same situation here as with the others. This other piece is just sort of to help you visualize the process, but you're always going to pick your limits off of the original picture before we drew any of this other garbage. Okay, so this is not a hard integral to do once you have it. You know what? We're not going to waste your time. I'm just going to make it fast. This ends up being this, right? I simplify this guy. I have to work that out and distribute my negative. Then I integrate this. It's just a polynomial. Where's the answer? Is it here? It ends up being 16 pi over 3. Okay. So you can work that out if you like. All right. So one thing I wanted to do before finishing off this video, or I wanted to finish off this video, is talk about the difference here. Remember, between this and the other method, the confusing thing, well, the most confusing thing sometimes is, am I integrating with respect to dx or dy? Because they're opposite, right? They're opposite. The washer method and the shell method are opposite with respect to that. If I was doing this with the washer method, I'm going around the x, so I would be integrating with respect to dx. But the shell method, because you're thinking about the thickness of the wall, where it's the height, you're going to be integrating with respect to dy. So let me make you a little chart, or let me make a little chart, and then you may write it down in your notebook to kind of clarify that. Okay. So, if you remember, for the washer method, or well, let's just do this. We have two options, right? Wow. We can do around the x-axis or the y-axis, or any, like say we have a horizontal line, right? So a horizontal line would be a line y equals some constant. A vertical line is going to be x equals some constant. So if you're doing it one way or the other, that's fine. Let me see if I can like make that a little bit better. Sure, not really. So for the washer method, as I just said, if we're going around the x-axis, we partition the x-axis, meaning we're integrating with respect to dx. And what we end up with when we draw that washer is we're imagining vertical strips that then go around and become the disc. Whereas for our shell method, like the one we just did, you are actually ending up partitioning the y-axis. So you're integrating with respect to dy. And that ends up being horizontal strips. If you look at those examples, the two where they showed you how it goes around the dx and versus the dy for the washers and the shells, you'll see that in one it's one way and one it's the other way. So same thing here, but backwards, of course, because if I'm going around the y-axis and I'm using these washers, I need to partition the y-axis, which means I'm integrating with respect to y. And so my strips are going to be horizontal, whereas for the shell, like the very first example that we did, we need to partition the x-axis and go dx when we're using the shells. And then that ends up being vertical strips. Okay. So hopefully this helps make it at least a little bit less confusing, because I do know that I say, oh, hey, use a picture and imagine the thickness and whatever, but sometimes it's very hard to draw the picture in a way that looks good. I mean, you can see I do a terrible job, and I've been doing this for years. So I don't know. I'm not an art major. What can I say? Doing my best, and I know sometimes, like, I find that when you draw it and just try to think about it, it does make it clearer, but you can always check on the chart to make sure you did it right.